Fans perform most efficiently when air flows straight into the fan and straight out of the fan. When air doesn't flow evenly into and out of the fan, performance drops. We call those performance drops system effects. The system is the path through which the air is pushed and pulled. Differing systems affect fan efficiency. If the fan can't run efficiently, operating costs can skyrocket. Example: two fans with 15-inch diameter wheels located on top of a restaurant are used to exhaust kitchen smoke and fumes. These fans are required to move 6,000 cubic feet of air per minute, or CFM, 16 hours a day. Fitted with poorly designed inlet boxes, the fans run at a higher speed, use more energy, and boost electrical bills by $1,600 per year. Example: a 36-inch fan capable of moving 18,000 CFM was installed with an elbow at the inlet. Moving air through this inefficient system increased energy use and energy costs by $6,100 per year. Example: a 49-inch fan was right for the job, but it was installed with an abrupt elbow at the outlet. The result? A $9,800 increase in the annual energy bill due to the increased fan speed required to overcome this system effect. Fans can use more electricity than all of the other system equipment in the plant or building combined. Each additional unit of horsepower costs about $1,000 per year. Clearly, system effects can be a big drain on profits. Deficiencies in airflow are usually overcome by increasing fan speed. But consider this: a 5% speed up of a 100 horsepower fan causes brake horsepower to rise to 116. That increase results in an additional energy cost of $16,000 every year throughout the life of the fan.
The typical plant manager doesn't think about his exhaust systems, his supply systems, and hence he's not aware of how much power they consume. If he were, he'd be shocked, and he would make sure that his present systems were redesigned and his new systems were designed to give him maximum airflow at minimum power cost.
Our fans are recognized in the industry as being a top quality product, and that stems from a design which centers around safety first and also involves minimizing the energy losses and maximizing the performance of each design. When we test fans, we test them in accordance with AMCA standards. AMCA is the Air Movement and Control Association, which is recognized as the authority in the fan industry. No matter how well a fan is designed, if the system is poorly engineered, there's no way the fan can perform to its fullest capabilities.
At our AMCA registered lab, we can demonstrate how system design affects fan efficiency. To maximize inlet efficiency and fan performance, air must be drawn into the fan with an evenly distributed velocity profile. With this forward curved 8-inch fan, the MagnaHelic gauge shows we're generating 1 inch of static pressure under these ideal conditions. For the purposes of this presentation, we'll use this ideal reading as a point of reference. Uneven eccentric airflow causes turbulence. Turbulence in turn reduces fan performance. We can simulate eccentric flow in the lab by attaching a poorly designed inlet box. The pulsation or surging sound you hear is caused by disrupted airflow. That means the fan is not performing at peak efficiency. The MagnaHelic gauge shows a performance drop of roughly 1/2 inch static pressure from 1 inch all the way down to 5/10 of an inch. In this example, the weight and the velocity of the air work against the fan by forcing air past the fan inlet. The turbulent air flows back to the fan inlet. Such poorly designed inlet ductwork is unfortunately all too common. A properly designed inlet box improves airflow into the fan and reduces turbulence. With the right kind of inlet box, performance losses are dramatically reduced. That translates into energy and financial savings. But poorly designed inlet boxes are not the only way a system can go bad. Fans work by changing the direction and velocity of the incoming air. If air is spinning in the same direction as the wheel, volume and pressure are reduced. If air is spinning in the opposite direction of the wheel, brake horsepower and noise increase. Fans work best when air flows straight into the inlet. The corkscrew effect created by two elbows positioned too closely together results in a performance drop of 0.3 of an inch of static pressure. Poor inlet connections produce losses in performance, but if space is a limiting factor, you have several alternatives. You can use a factory-designed inlet box and install corrective devices in the ducts, such as vanes, to minimize eccentric and spinning flow. Or you can increase the fan speed. But remember, with increased fan speed comes increased energy costs. Under extreme field conditions, you may need to install corrective devices and increase the fan speed to achieve the necessary levels of airflow. Your choice will always be to design the system, including the inlet ductwork, to avoid the expense of increasing the fan speed to compensate for system effects. Proper system design is the best way to maximize inlet efficiency. The fan inlet is just half the story. The other half of the story is the fan outlet. The transition made at the fan outlet affects fan performance as surely as the transition at the fan inlet. Fans are tested with straight outlet ductwork. Unless your installation includes a straight run of ductwork at the fan outlet, the fan cannot operate at its full tested capacity. When there is no outlet duct, air can't discharge with even velocity. The air, which has weight, is thrown to the outside of the scroll. Air requires several duct diameters for its velocity profile to even out. That's why outlet ductwork is so important. The use of elbows at the fan outlet should be avoided, but if you must use an elbow outlet, make sure the turn in the elbow follows the same direction as the fan wheel rotation. In this way, your loss will not be as great as it would be if the elbow turns against the direction of flow. As you can see, efficiency can be lost when the elbow is turned against the direction of flow. For maximum outlet efficiency, of course, air should be discharged through a straight outlet duct. Straight is the word to keep in mind when designing inlet or outlet ductwork, because fans are able to develop more pressure when they are fitted with straight ducts. Any abrupt turns at the inlet or outlet will result in system effects that significantly disrupt airflow. Of course, even many of the worst designs can be made to work by increasing RPM. By increasing fan speed, it's possible to meet airflow requirements. Problem is, you pay the penalty for such system effects in the form of higher electrical bills. When a system is not performing up to anticipated standards, the tendency is to blame the fan. That's natural. It's difficult to see how non-moving ductwork could be part of the problem, but it is. The New York Blower Company has been moving air for over a century. As charter members of AMCA, we pride ourselves on precision testing and rigid quality control. Our equipment is rugged, efficient, and internationally recognized for quality design and manufacture. But even the best fans require a system designed to minimize eccentric spinning airflow at the inlet or uneven airflow at the outlet. System effects are all too common, but with correct design, you save energy and money with air-moving systems that run at maximum efficiency day after day, year after year, throughout the life of the fan.